Hi, everyone watching on YouTube. This is a continuation of the introduction to statistical learning in Python, with the second week on the classification chapter. Last week we covered the logistic regression, the multiple logistic, or the multinomial. I can't remember exactly what we deep dived in. We mentioned generative models, and then we looked at a comparison, like an empirical comparison of the models. And then this week, we're going to do a bit more of a deep dive into the generative models and maybe try to motivate kind of how they work and what is also like, why do they work? And we'll start with Bayes' theorem. So probably if you're taking this course, like you've seen Bayes' theorem a lot. It might not always be top of mind. I don't think it's the most intuitive thing for most people. Often it gives an intuitive answer, but it's not always like easy to see why you have like A conditional on B and then B conditional on A, etc. But all it really is, or all it's used, what it's mainly used for, is to give you an indication of how to like update your hypothesis when you get some new information. That's kind of like the whole idea. You could be trying to figure something out, some information that gives you like an estimate of what you're trying to figure out, and then you get some new information. It's like, okay, well, what do I do with that information? And Bayes' theorem just like helps you get that information, update your estimate, and then you've got your estimate afterwards. And I wanted to work through an example because we're going to be using this. We're going to be taking this theorem, we're going to be applying it to a bunch of models, or a bunch of models are basically going to be applying it. And I think it will be helpful to have like a worked example in mind. So something that made sense to me was just like, okay, if someone just came along and asked me to like guess whether a certain person was an astronaut, and I didn't get any other information, the obvious thing to do is just try to figure out, okay, how many astronauts are there in the world? And then how many people are there in the world? And then just like divide and get the proportion of astronauts as of people, which is a very small number. And that would be like my hypothesis. Like if I don't have any extra information, that's the reasonable thing, kind of in my opinion, to do. And there's a little bit of a gotcha where people often say like, well, the fact that someone asked you if it's an astronaut, maybe you should think it's more likely. But let's just say in most cases, you just want to say like, okay, no, this is just like the baseline probability. I've got no other information. So that's my estimate. But then you get given some new information, and it's that the person works at NASA. Like that is very useful information. Probably like about as useful information as you're going to get, right? Or they work at like, I don't know, the Chinese Space Agency or whatever. Like someone come along and tell you that, and that should make you really like update your probability estimate. But how much kind of should it do that? Well, that's what we're going to like want Bayes' theorem for. The key parts of Bayes' theorem are that this is what we're trying to figure out. Like this is the posterior. So like after we take the information that we learned, like what is our estimate? And we get that by multiplying like the likelihood by the prior, and then kind of like normalizing by the evidence. But the main thing is really like is up here. If this is like given that someone works at NASA, are they an astronaut? We then look at, okay, flip it around and say, given someone is an astronaut, so like how many astronauts are there in the world? Like how many people at NASA are astronauts? And we take that, so we're looking for like AB here, and we flip it and we put BA here. And that's the likelihood term. And in the generative models that we look at later, it's this likelihood term that we're going to spend most of our time trying to estimate or trying to figure out. Okay, but maybe helps to actually just like plug in some numbers. So I sort of made some of this up, but I also did get a couple of bits of information off of NASA's website. And the likelihood, so there are like 200 astronauts approximately in the world, and 47 of them work at NASA. So like, given that someone is an astronaut, it's like 47 out of 200 of those are going to work at NASA. The prior, so what we used to think, was like, okay, there are 200 people and there are 8 billion, 200 astronauts and there are 800 billion people in the world, or so 8 billion people in the world. So our like estimate before we know anything is very slim. And then the evidence is like, okay, what we got given is that the person works at NASA. So there are 18,000 employees at NASA. So the chance that like a random person works at NASA is 18,000 out of 8 billion. You can kind of see what happens if you just do some like algebra to cancel stuff out, is you get these 200 terms that are in the denominator here in the numerator, they just cancel out algebraically because this is a term. And then you've still got like sort of like a fraction in the denominator, which is normally quite not very nice to work with. So you tend to just invert that. So dividing by a fraction is the same as multiplying by the inverse. So we multiply by the inverse, and then we've got the 8 billion term is on like the denominator one and the numerator the other, cancel them out, and then we get our updated estimate. And that is 47 out of 18,000, because the likelihood that someone is an astronaut now, given the information we have, is the number of astronauts working at NASA, like as a proportion of the total number of employees at NASA. So that was like why we have this term here, that like we flip. We're looking for the probability that you're an astronaut given NASA, but we go the other way and we go NASA given astronaut, then cancel stuff out, and then we get our nice, neat probability estimate. I do think often the formulas, like, and this is why I try to add the braces and do it in code, is often still for me, formulas are always more difficult than code, or especially like unannotated formulas are more difficult than code. So basically we're just doing, in this bit, we're just doing this little bit of code. It's like, what's the likelihood, what's the prior, what's the evidence? And then the posterior is just the likelihood times the prior over the evidence, and then our estimate. And that is Bayes' theorem working in a concrete way. And I hope that kind of motivates for like, where do these conditional probabilities come from? Like, why are they both there? And how are they going to be useful later? Because we're just going to do the same thing with generative models, but the likelihood is going to be something different, or something quite a lot more complex than like this little term here. But that's all we're going to try to do. We're going to try to estimate the likelihood, plug this stuff in, secretly stuff will cancel, and then we'll get our estimate. Okay, so moving on to generative models and Bayes' theorem. Before we get into the generative models, like, why are they called generative models instead of, say, logistic regression, which is like a discriminant or like discriminative model? The generative models are trying to estimate like a probability distribution. And if you can estimate that probability distribution, then you can generate new data. And that's kind of it. Like in logistic regression, you're trying to figure out the posterior probability, not say like this probability term. And once you can learn that, or you can like approximate that, but that doesn't mean you can generate more samples. Whereas if you learn the probability distribution itself, you can generate more samples. I don't know if it's like nowadays you wouldn't really use this term just because like generative AI is just what everyone thinks of as generative AI. But that's why these are talking about generative models, or like as classification models. Okay, so keep our Bayes theorem in mind. Generally, what we're going to be trying to do in the classification case is say like, okay, given some features for an observation, like given a data point and the values for the features or a feature, it's like, what class should I put that into? Maggie spoke quite a bit about that last week. And that will then look like this. So that will be your posterior over here. It's like, given the feature, what's the class? To figure that out, you'll do the similar thing to what we did with the astronauts. You'll go, okay, given the class, what are the features? Like, how do the features look for that class? You've got your prior probability, which is just like, what is the class? So as like a proportion of the data set. So for each like level of the categories, what proportion are they in the data set? And then over here is like, okay, how many of like the features, or what's the proportion of the features in your data set. And that will get a little bit more complicated. We'll kind of talk about like not exact values, but for now, just try to take the astronaut example and think this is the same thing. This is how it kind of will all line up. The evidence term, like you just get from Wiki, this is also called like marginal likelihood or model evidence, like depending on which background you come from, you'll have had different terms. But then if we can get the posterior, so if we can estimate the probability, we'll just essentially create a Bayes classifier and recall like the Bayes classifier is just like, what's the highest probability label? It's like, we'll assign it to that. Just like a shorthand for that idea, like take the argmax of the probability generating function and just that one is the label. Okay, normally though, we'll be looking like not just one feature where this is a scalar here, it's just like one value as a feature. Normally we'll be like looking at a vector of features, so multiple dimensions going into our model. And all we're really doing is like, it's replacing this term and this term and this term. And instead of having a scalar, we're putting in a vector. Again, posterior, like the prior evidence, they will be, this is what we're trying to figure out. And these are the tools like that we'll be using. These are values we're trying to plug in. But okay, if you think about it in the generative case, like the prior is going to be really easy. You're just in the training data set, you've got like a list or like a column that comes down and tells you like it's this class, it's this class, it's this class. You can just count them up and you can divide them by the length of the list, and you'll know like for each level of the class, like that's the prior. It will just be that as a proportion. For the features, I will say it's just a little bit more complicated than it like lets on here. So we're just going to ignore that for now because we do talk about it in a minute. And then this term, like just to really spell it out, is like get the class, so get all of the examples of each like level of the classification and look at all of the rows that apply to that. And there you've got your distribution of the input features. So that's like the term. Okay, the book does use like different notation. So like just being aware of what the book's notation is. You've still got the posterior here. You've got f sub kx is the likelihood, and the book actually I think has it on the left-hand side or the right-hand side. I just switched it to the left-hand side because it's like what I'm more used to. Then you've got your prior on the right-hand side, and that's just the class labels. And then you've got like the evidence that we're going to dip into now. So the why do we use a density function like instead of just exact values for features? I think this was before I actually like this is probably actually a good time for me to take a breath and to ask like an open question. It's like, why are we talking about density functions here instead of exact values for features?
Is it because when you have a data set, you don't have every sample in the population, and like one of the assumptions of this is that like features are normally distributed, or yeah, features are normally distributed. So like the data set you have isn't every example that exists. It's just a sample of a normally distributed density function.
Yeah, I certainly think it's linked. We're not quite onto LDA yet, where that assumption does come in. But like there's almost like it's like a bit simpler than that. Is when you've got continuous inputs, an LDA like will normally take continuous inputs. So you know, like floating point numbers. The more dimensions you add to your predictors, like input variables, like the less likely it is that you've got more than one instance of those features, like for exact values. And if you're, it's kind of like an idea in maths where there is an infinite number of numbers between any number. Like you can just keep on like putting decimals in between stuff for infinity. And that's, I can't remember what it's called, but it's like, that's like the density principle of numbers. So if you've got like some like unrounded continuous features and you've got like one value is like 0.3784521, like you probably don't have any other samples in your data set that have that exact value. So what you want instead is to get like the nearby values within a range. And you do that by looking at density function. You can look at intervals, like small intervals around your features. And it's because otherwise you'd always be working with like a sample size of 1 for those input features. But if you can use not exact values, but like a small range inside the like density function, then you've got nearby values for input features.
Yeah, I think that's kind of like similar, kind of getting at the same thing of like you don't have every possible value in the population. You have a sample, so like the density function gets at every value. Yeah, like the decimal places or whatever.
Yeah, I think say even if you had like kind of say, well, if you had the population, it's like okay, you don't actually need to like estimate anything anymore. You just look up the value. But you could even have every single value in the population, and you could still have no examples of like those exact values of input features because your input features are continuous. And you kind of need to not have it so that every single value is like the only time it's been seen. Because then you have no, it's like the difference between stuff being really close, which is like more likely than stuff being exactly the same. Like I think on one of the, I got some additional resources that I'll link in the bottom, but it made the point like just the likelihood that you have any other values that the exact same when you have continuous is essentially 0. And that is bad. I didn't get on to looking at Mahalanobis distance, and that is kind of like when you get onto the multivariate case, it's like how do you tell the distance between things? So that's a to-do that will not, in fact, be done. Okay, so moving on to like away from just like generative models in general and what they're trying to do, linear discriminant analysis. Before we jump into formulas or thinking about anything, like at a very high level, what it's trying to do is like just draw a line through stuff that separates two groups. And the idea is that you draw the line at the point where two groups are like equally likely. So you can see in this, there's like this like normally distributed data. It's got like it's centralized and everything at 0. It's got like, I'm pretty sure it's just got standard deviation 1, but it's got different means. So the data like is sent in different places for each one. If you draw this line, like to the left, it's like going to be green, and to the right, it's going to be pink. But on the line, it's like 50-50, like half of the data exactly around this line will be like pink and half will be green. And those ones that are slightly over, some of them will be misclassified, but that's what you're trying to do. You're trying to find this point where it's like equally likely for the groups. And I think geometrically, you can just see why that's a good idea. If you draw that line anywhere else, like you won't do as well. Okay. So yeah, sorry, let me just gather where we were. Yeah, and in the Bayes theorem lens, like LDA is like purely a method for getting that likelihood. We don't need to get the prior, we don't need to get the evidence. It's like fine, estimate the likelihood. Okay. Lots of places just say that estimating like the likelihood for like the probability dense function is difficult. They're like always maybe expand why. I'm not really going to expand why. I do have in a footnote some very high level things, but it essentially kind of goes back to that point about like as you add more dimensions, like your data gets sparser and sparser. But it's also the case that for lots of distributions, it's really hard to solve them analytically, which means you have to use like a numerical optimization technique to find the parameters. Depending on the distribution, that's either like completely feasible or like not tractable to do analytically. LDA makes some assumptions, right, that help with this. It says like, okay, this is difficult, so I'm going to make some assumptions. And if I make these assumptions and these assumptions hold, I just basically give you mathematical guarantees that I can help you segment this data well, or like I can reduce the dimensions for you in a nice way, depending on what task you're doing. If the assumptions don't hold, like it doesn't mean don't use the model. We briefly spoke about this yesterday. It just means you don't have the guarantees. Like you don't have the mathematical guarantee that the output is going to be solid or that it's going to do a good job of, say, like separating data, but it might empirically still do a good job. So like you run the model, you test it. And what are the key assumptions? Like the two key assumptions are that the input features for each class. So remember, we're trying to get the likelihood. So that means getting all of the observations for the class and look at the input features. Like those input features follow a normal distribution, which in the like univariate or the single variable case means they'll look something like this. Or if like the standard deviation say is higher, then they'll be like wider rather than taller. But you'll be able to like describe them with a bell curve one way or another, either a thin one or like a wide one. When there's only one predictor, that does literally just mean like the distribution looks quite like this of that one predictor. Again, could be wider, could be shorter. When there are more, it means that it follows like a multivariate normal distribution, which you are like extending this idea into, instead of it being across a line, like being in multiple dimensions, you can still visualize in say like 2 dimensions and 3 dimensions, but after that, you can't do it. If you go to Wikipedia, you'll get some nice like views of what like a multivariable normal distribution looks like. I'd advise anyone to like go and look at that stuff if you feel you want to or you need to. And then the second assumption, and this is kind of the one I think we were speaking about most last week, is that the input features have like the same spread. And that is, if you look at these two, like if you look at their distributions, they do have the same spread. And if they didn't, if you think what would happen is you couldn't draw this line like this. If this one was just like had a lower peak but had a higher standard deviation and was very wide, you couldn't draw the line exactly like this. You'd have to do some other stuff first. Sanjay?
Yes, don't forget that it's always possible to scale before. So basically, we make them to be the same, we make them to be distributed like that, so sometimes it's just a matter to clean the data so they are what we expect them.
And
we standardize them at the beginning of the process.
Yeah, you can do transformations on on parts of the data or not. And there's a really good book that I didn't get time to re-implement the code, but they actually show you like how linear, like LDA rescales the data to find the lines. I've linked that book at the bottom. It has a really good code notebook, so I would advise people go through it. But yeah, LDA is kind of like gonna, like that's one of the things that it's gonna do. Okay, so I wanted to like motivate maybe this normality assumption and the covariance matrix. So just the reason it's like much quicker computationally if you assume a normal distribution is that you can just solve things very fast analytically. You need to know the mean and the standard deviation. And if you know that, you can get the exact probability that an observation came from one group or the other. So if you think you've got group 1, the mean height is 160 centimeters and standard deviation is 5. And in group 2, the mean height is 150 centimeters, standard deviation 5. If like a person comes along and they've got a height 166 centimeters, you can calculate analytically, like you don't need to do any optimization. You can just plug in the values for like the mean of the group, the standard deviation, and the observation's height, and you get the exact probability very quickly. So you can say that It was like a 3.9% chance that person came from group 1 and 0.05% chance from group 2. It's like, leaving everything aside, it's just a mathematical fact that it's much more likely that the person came from group 1 than group 2, and you just calculated that very quickly. Contrast that, say, with a person who's right in between the two groups and their means, then it becomes like equally probable that they're in either group. So if you're doing the LDA, it's like, that's, in my example, that's where your linear decision boundary is going to be. It's like exactly 155 centimeters. Anything lower, you'll assign to group 2. Anything higher, you assign to group 1. And like, very easy to calculate. Okay, there is another thing that you can prove, that if stuff is normally distributed, then if it also has like the values also share their covariance matrix, then the decision boundary is linear. But as ever, it's like, that's so easy to show that that will always be left as an exercise to the reader. And we move on to like motivation for the covariance matrix. At this point, does this stuff help motivate it? Like, is this, as like a concrete example, like, is this helpful to think of?
I'm thinking aloud a little bit here, but I was kind of struggling with the idea that, basically for any question that was like interesting, we'll have picked features or predictors that, like maybe like the reason they're good features or predictors is like almost because they aren't normally distributed within each class, or don't have different, or because they have different variances. Like you could imagine, I mean, even in this height case, like maybe group 1 is tall because like you got assigned to group 1 if maybe it's the group that can ride the really big roller coasters or something like that. I don't know, like and so then like height wouldn't be normally distributed to have a cutoff, or like I don't know, like if you're assigning people to neighborhoods and you're like, okay, like, the chance that this person is from this neighborhood maybe has to do with their different demographic features, but like neighborhoods are different. And so like actually one neighborhood, doesn't have a normal distribution of, feature X or what. I don't know. I felt like I was trying to think of good cases where this would be like a pretty solid assumption to make. It seems like most of the time it's going to be a tough one. And I guess maybe that's not a problem because like maybe this is a robust to this violation, but it struck me as awfully strong.
Yeah, I think there are some things in the world that happen to be, there's a lot of things, say, that happen to be like normally distributed. Yeah, I like there if you Google them, there are just like tons of examples. They tend to be like physical things, or rather than say like attention. There are just like, as an empirical fact, lots of things, but for sure also there are lots of cases where this will not be the case. Go back to Sandrine's point again. Say if you've got something that's like exponentially distributed, then you can like log transform it and you get a log normal feature. You have to do some stuff afterwards to like get the prediction out and interpret the coefficient because it's like log transform. But you can make a lot of stuff normally distributed as well if you need to. Doesn't always mean that you should. Ether, sorry, really.
Well, I was gonna say, like you kind of said it there, like I have always thought anyway that basically everything is normally distributed. Like I'm sure there are cases where things are not normally distributed, but yeah, like you say, if there's a height and there's a cutoff for roller coasters, sure, like maybe you're cutting it off like kind of right at what the mean of like a height distribution would be. But yeah, you can like transform it for that kind of thing. But like even if everything is kind of like basically like if a distribution has things that are like basically the same, it's just like a narrower normal distribution, or like if things are like, oh, they're really not the same, it's just like a wider normal distribution. But like you still have the tails and you still have like maybe like a longer flatter. But I would have always kind of thought that, yeah, like almost everything is normally distributed, almost as a rule.
And in real life, we are removing the outlier. So basically, it's just a way to clean everything so it ends up to be normally distributed. It's yeah.
Yeah, I don't want to jump into removing outlines, but that is true. A lot of time they will just be cut. Yeah, I think the thing with normal distribution stuff is, like I said, it's often stuff in the physical world. But if you think about, like, if you were getting the distribution of sales by author, that is like super skewed. It's not going to be normally distributed. Like, there are lots of things like wages or whatnot. Like they become very, like, there's lots of things you'll find that won't be normally distributed as well. And there's a lot of distributions. There's more distributions than I think anybody could name.
Yeah, but I guess like you can transform then, so that like you say, like you can force things to be normally distributed.
Yeah, normally normally it's like some things like exponential, you can do a logarithmic transformation, getting rid of them or things like that. Often you'll find like stuff is log normal distributed, but there would be, I don't know, there would be times where you'd be fighting to like make something normally distributed when it's not. And often the answer would be like, okay, use a different type of model, because there are models that are built for like a gamma distribution, like exponential distribution, Poisson distribution. Like there are ways. The big idea is the central limit theorem, which is like the mean of not normally distributed values. Like if you sample means will approach normal distribution. I think, yeah, we'd get a bit further from kind of where we need to be if we go into that. But yeah, a lot of things will be normally distributed, but there will be things that are not. I'm going to try to
I found
up.
everyone's comments there very helpful. Thank you.
Yeah, I'm going to try to speed up so that we've got good time for Sandrine, because you've got your thing too. So the motivation for the covariance matrix, like, okay, TLDR is just like ensure that stuff is linearly separable. That's what LDA wants to do, is make linear separations. So you've got the normality assumption, like that's fulfilled, and this covariance matrix one is, then stuff is like generally going to be linearly separable. But to actually motivate like that, it's like step back a bit and think about it. Like variance is just like single variable. Covariance matrix is extending variance into multiple variables. If you think about what variance is, like say this data here, and this is from a pretty good little thing that I've linked to, and it's in the resources. But the variance, say along X, like that can tell you about stuff that's like horizontal spread. And the variance of Y can tell you about stuff that's vertically spread. But variance cannot give you information about diagonal spread. Like mathematically and by definition, it just cannot. Covariance can. So when you see stuff, and this is like a linear relationship, because as X increases, like tends to be the case, so does Y. You need to be able to like understand, or the model needs to be able to understand these diagonal relationships, like these linear relationships, and variance doesn't do it, but covariance does. And then, okay, you get your, like, this is what covariance matrix actually looks like. If you're a bit eagle-eyed, you see like the diagonal is the variance, and then the anti, like off diagonal is the like covariance. Don't worry about that too much. But another way of thinking about any matrix, like linear, is transformations through space. So this is the covariance matrix, like for this data. And you can see like they are linearly correlated positively. Like as X increases, like so does Y. This is when they're not like positively correlated, but they are negatively correlated. So all you do is you minus one the off diagonal. And then this is the covariance matrix for data that is like, it's just not linear relate, like there is just not a correlation. And this is what the covariance matrix would look like. And here again, there is not a linear correlation in this data. I think kind of that's the whole idea. Is like, that's why it's like, if you do have these two things, It's like LDA will be able to split your data up for you well linearly. And if you don't, well, it's like maybe it will, but maybe it won't. I think what I wanted to do is come also, I'm actually going to skip this because I've kind of spoken about it already. If we get back to the formula, so for LDA, but in the case of one, we've got posterior, we've got likelihood, we've got prior, we've got evidence. Likelihood looks kind of nuts, but this is just like, go on Wikipedia and look at the probability density function for like a Gaussian distribution. Like this is essentially it. So if you're familiar with that, it will be like, yes, okay, look, that's what it is. And if you're not, it's like, okay, there's time later to like figure it out and stuff. Yeah, I'm gonna. I think it will take too long to really go through this stuff like a bit more like fully. So we'll just say like to make our predictions with LDA, what we need to get the likelihood, like what we need to get values for is just like two parameters. Those parameters like hidden in here. Yeah, Sandy.
You know, yeah, maybe I could do my slide now because it's exactly what you are talking now in a sample example.
Yeah, let's go for it. Let me stop sharing.
Okay, so let me share my screen. Okay, let me know. Okay, let me know if you see it. Do you see it?
Yeah,
I think it's working.
Okay, perfect. Okay, so basically, I just want to explain when we are going to use this one. So basically, I use LDA a lot when I was working because I was in market research. And in market research, we like to do some customer segmentation. And customer segmentation is unsupervised learning technique that we are going to see at the end of the book. So basically, just a way you have a ton of books or ton of customers, and you are just trying to find the best way to sort them, to do bucket. And the bucket has to be robust statistically and also to make sense for the client and the business. So it's a bit of art and stat. So, but at the end, what the client want to do? They want to be able to predict. And if they don't want to predict like we do in Python, we're just doing a predict. They want to have something easy for them to do. And they want an Excel tool because they want something very, very easy. So they are going to assign the segment in another data set and could be in anything, even when they don't have the original variable, we don't care. They just want to assign. So basically, because in LDA, we assume that for each different class, the covariance is identical, everything is going to be easy because everything is going to be linear. So it's what we have just seen with Jack's slide, is that, okay, we have this nice formula, and but this nice formula actually is just a sum product in Excel. Why? I will explain later because maybe it's easier here. So basically, what are we really going to do? We just have, it's just a simple example that is why I wanted to talk now, because basically it's just, so at the end, because all the simplification of the formula, when we remove the variance, the covariance, because it's the same for everywhere. So, and we just want to find the max. So we just want to find the max. So basically we are computing this delta K for each class. In my case, we have 3 classes. So here we have the number. I don't see the camera the way I'm sharing, so I don't see if somebody is asking questions. So we have here, it's the X we want to classify. Here are the our linear coefficient, and we are just doing the computation. So, and we are taking the max. Basically, it's another way to see the frontier, but basically what we only care is where is the maximum. Where it's the example we have seen previously, so we just care about that, and it's very, very easy to implement. it's just some linear computation, and we find the maximum. There is also case when the client, they don't want to know what is the segment, but they want to have the proportion of the segment, which is also easy to get because basically we just look at we just take what is, because we just assume that is a kind of probability, and we just compute in what is the percentage. So maybe, for example, this one is maybe 75%, this one can be maybe 12%, this one is 1%. So we just give him some kind of probability to belong to a class. And everything is just done because we have a straightforward math. It's a sum product in Excel, and it's how in real life people, they use the LDA. So I'm hoping that it's all I have. I'm hoping that it helps you to understand exactly why it is well liked, because it's very simple. Don't know if you have any question.
Oh, perfect. I do think maybe in the formula as it is there, like you've got the input feature vector, and then you've got W, and maybe like
yeah,
what's,
but yes,
W?
It's just because at the end, at the end on this one, the covariance remove. So at the end, you just have the x and the coefficient in the code. You could get the coefficient of the LDA. There is a way. I didn't want to introduce any code, but basically we need the coefficient given by the LDA to do that, and it is okay. And if so, it is why it is really well liked, because it means that you could assign you could do the assignment in Excel, in any tabular.
Yeah, cool. That's cool. Because there is there's the like Fisher discriminant kind of thing with it like all comes
Fisher,
from, right?
yes, okay. Fisher discriminant, okay, but Fisher discriminant are a bit different because the Fisher discriminant are coming more from the they are not more used in the PCA. I saw, but I think they're a bit different.
Yeah, well, what it's in LDA for just the two binary classification, like group or not group. There's a formula that looks a little bit similar to that, and it's like the between group sum of squares over the within group sum of squares. And in that they use W as the like within group. And I was just wondering what the W here, but the W here is just like in a linear model, right? With like just like the weights, whatever the weights are.
No, it's not weight. It's just coefficients that you could grab from. You could grab from the, if you do LD, if you do it in Python, after you can get the coefficient. But they are not Fisher coefficient, but they are coefficient. Yeah, because I asked ChatGPT about that because I saw first maybe they're Fisher, but they are not Fisher.
Yeah, no, so not like Fisher, but there's Fisher discriminant, like let me get the there is this formula that I'm talking about, Fisher, and this was actually in the reading for this one. You've got where's it gone? Fisher. Let me just get the formula, because it's another way, I think, of like thinking about what LDA all is. Can't find the thing that I was looking at now. I tell you, I'll try to find this. But Meg, do you want to go through? We've got 10 minutes. So we've got time for one of the exercises.
Sure. I pulled like one of the conceptual exercises, one of the applied exercises. I don't know if we probably shouldn't do like the applied together unless people have like Python up and ready to go. And then the other one I pulled was just about like the differences between LDA and QDA. Just as kind of like discussion questions, I guess. So the first one is I'm looking at exercise, or what are they called? Not exercise. Yeah, exercise number 5. If the Bayes decision boundary is linear, do we expect LDA or QDA to perform better on the training set? And then which one would perform better on the test set? Which is something Jack just talked about. I can also put it in the chat.
I feel like I've been tricked or something, but it feels like it would perform better. LDA would perform, you know, maybe they would perform similarly with respect to bias, but LDA would have tighter variance, I think, right? Just because it's kind of, matching the underlying features of the data.
I think so. I would agree. Any other reasons for anybody else? And then like same question for if it was non-linear. Like it's kind of in the name.
Yeah, I think just the opposite. I think, well, maybe not quite the opposite, but like I think we'd be worried about bias in the case of LDA, and maybe and less so in the QDA case.
Yeah. So if the decision boundary is non-linear, that kind of suggests that the covariance matrices aren't the same. So then QDA would perform maybe better.
And then I can.
And do you think there would be a difference between how they perform on the training versus the test set? Or would you expect similar results for both?
I think non-linear, I would expect similar on both.
Yeah.
Like QDA would perform better on both.
And I think QDA is always going to do, or no, excuse me, LDA will do okay, I think, on the test in the second question, but it probably will, sorry, reverse that. LDA will do okay on the training set, probably, but maybe quite a bit worse on the test set. That'd be, I think that's right, because LDA we're worried that it's not flexible enough. So when we introduce new data, it might just kind of miss the mark by a wide margin. I think that's right.
It should often be the other way, right? The higher variance predictor, like QDA, will do better on the training set because it will like fit the training set better because it can wrap around more. But often, even though it's worse, like on the training set, like the low variance, high bias predictor like LDA might do well on the test set because it doesn't overfit the training data. So it's not always the case, but like often the bias variance training goes that way.
So if it's in the non-linear boundary, it's the same.
It depends if they're from the same. I think if they're from, often the whole idea is like if they're from the same distribution, like if the training and test are actually from like similar distributions, like the training and test error will be very close, and then the QDA should do better on both the training and the testing. If they're from slightly different distributions, like if over time distributions move, like overfitting the training set will probably actually do you more harm in the testing. So the lower, like the linear one actually will be like more reasonable the further away you get from the training distribution. Often, no, not like no hard fast rules, but
Um,
let me stop the recording because I think we're at quite like a natural end.